Welcome children. So in this video we will see the part 4 of SHM. So in this part 4, so we are going to see steps to find time period of SHM. So we have a linear SHM and also angular SHM. So what are the steps to be followed to find the time period of linear SHM? Linear SHM means so the particle will be executing SHM in a straight line. So the particle will undergo translative motion. The particle will not undergo rotative motion. The particle undergoes rotative motion and then if it performs oscillations, then it is called angular acceleration. If the particle just translates and it performs oscillations in a straight line, then it is called linear acceleration. So now, so what are the steps to be followed to find the time period of linear acceleration? These are the steps, children. So clearly I have shown the steps to be followed. So locate the equilibrium point. Equilibrium point is the point where the net force acting on the particle is zero. Displace the particle slightly away from its main point. So in that displaced position, find the force acting on the main point. So find the force acting on the particle towards the main point. Always you should find the force acting on the particle or system towards the main point. That is the force responsible for the accession. That is the force responsible so to make the particle execute accession. So after that, after finding the force, equate that force to ma, F equal to ma from Newton's second law, then find modulus of x by a, then time period is given by 2 pi root over modulus of x by a. Why 2 pi root over modulus of x by a becomes so time period? Basically time period is t is equal to 2 pi divided by omega. So here 1 by omega value is equal to root over modulus of x by a. How we get that? See children here. You get modulus of x by a as or root over modulus of x by a as 1 by omega like this. A is equal to minus omega square x. So minus 1 by omega square is equal to x by a. Modulus of x by a, modulus of x by a is equal to 1 by omega square. So that implies root over modulus of x by a is equal to 1 by omega. That's how the time period becomes 2 pi root over modulus of x by a. Okay, so here angular acceleration. So locate same way. Locate the equilibrium point. It is a point where the net torque acting on the particular system is zero. Displace the particle away from its mean point or equilibrium point. Find the torque in the displaced position. Here torque should be equated to I alpha. And here instead of finding modulus of x by a, find modulus of theta by alpha. So now the time period is given by 2 pi root over modulus of theta by alpha. Here root over modulus of theta by alpha is 1 by omega. So these are the steps to be followed to find the time period of linear acceleration and the time period of angular acceleration. Once we understand that, we go to spring block systems. See children here, in spring block systems we will see different situations. First we will see the simple one, horizontal spring block system. Suppose a spring or spring constant k is connected to a block of mass m. Then the time period is given by t is equal to 2 pi root over m divided by k. This is the time period of horizontal spring block system. Even for vertical spring block system also. Here m is the mass of the particle executing a section. That is mass of the block actually. Mass of the block, and so k is spring constant. K is spring constant. K is spring constant. So mass sometimes they'll give in gram or kg. K, the SI unit of kg is Newton per meter. So sometimes they give you the k value in dyne per centimeter. Dyne per centimeter also. Okay. Now Here, this is the equilibrium position. So what is the equilibrium position? It is the position where the spring has natural length. Away from that equilibrium position, so to what extent you pull the block or you elongate the block, same will be the amplitude of oscillation. So to what extent you pull the block, to the same extent it will go, the block will go this side. So that becomes amplitude. Now, springs in series. So we connect two springs in series, and so the combination will be connected to a block of mass m. Now what is the time period? In such cases, you have to find the effective K. So when springs are in series, 1 by K effective equal to 1 by K1 plus 1 by K2. This formula can be extended for any number of springs in series. For two springs in series, so you can solve this. You will get K effective equal to K1, K2 divided by K1 plus K2. Now see children, the time period is given by 2 pi root over m divided by K effective. This K effective is, so you substitute here. This is how you get the time period when springs are connected in series. Now, even springs can be connected in series like this in the vertical spring block system. Suppose this is one spring of spring constant K1, this is another spring of spring constant K2. Okay, together they are connected to a block of mass m. You can have any number of springs so like this connected in series, even 3 or 4, 5. Now the time period is given by same. So K effective is equal to K1 K2 divided by K1 plus K2, and the time period is given by 2 pi root over m divided by K effective. Now, how we get the formula when springs are connected in parallel? This is how springs are connected in parallel. When springs are connected in parallel, see here, these springs are in parallel. These two springs are in parallel. Even these two springs are also in parallel, remember. So you might be wondering why springs in the third diagram are in parallel. So they actually connected in series, no? Why they are in parallel? So many students will have a doubt. So I'll explain this. These two springs are not in series, they are in parallel. Because slightly displace the block towards left or right. So here I displace the block towards left by an amount x. When I displace the block towards left by an amount x, the first spring will get compressed. So the first spring will push the block towards right, kx. So or k1x is the force exerted by first spring. Now the second spring will get elongated. The second spring, since it gets elongated, it will pull the block towards it. So that pulling force also will be towards right. Now the total force acting on that block will be K1 plus K2 into X. So this is the effective spring constant K1 plus K2. So that's why they are in parallel. So in this slide I have shown you three diagrams. In all the three diagrams the springs are in parallel. So now once we understand that, now what is the effective spring constant when springs are in parallel? K effective equal to K1 plus K2. So now the time period is given by 2 pi root over m divided by K effective, that K effective. So you have to substitute here. Now you have seen springs in series and springs in parallel. Now there can be combinations like this. So few springs will be in series and few springs will be in parallel. Suppose for example we have a system like this. So there is a spring or spring constant K1 like this, and so there are two springs or spring constant K2 and K3, so together connected to a block of mass m like this. Now K2 and K3 are in parallel, together they are in series with K1. So effective spring constant will be like this. K2 and K3 are in parallel. K2 and K3 are in parallel. Together they are in series with K1. So this is the effective spring constant. Now this effective spring constant you have to substitute in this formula. T is equal to 2 pi root over m by k effective. K2 and K3 are in series. Together they are in series. So K2 and K3 are in parallel. Together they are in series with the K1. Okay. So once if we understand that, we go to the next concept, that is how to find the amplitude. How to find the amplitude in vertical spring block system. Very, very important concept. So how to find the amplitude in vertical spring block system? See children. Suppose there is a spring, so to which we don't connect any block, then the spring will have natural length. Now you connect a block of mass m and slowly release the block. When you slowly release the block, then the block will attain equilibrium position. The block will reach the equilibrium position. In the equilibrium position, so you can write this mg is equal to kx naught, kx naught. So that is the equilibrium position. Mg is equal to kx naught, or x naught is equal to mg divided by k. This is the equilibrium elongation. When you release the block slowly, but suppose instead of releasing slowly, if you suddenly release the block, then the block will go beyond its equilibrium position. When the block goes beyond its equilibrium position, so then it will execute SHM actually. Again, I will repeat this concept. So after attaching the block to the spring, unstretched spring, if we slowly release the block, it will come to equilibrium position. It will not execute SHM. But suddenly if you release the block, it will execute SHM. It will go beyond its equilibrium point. So beyond its equilibrium point, to what extent it will go, that will be the amplitude. So how to know or how to calculate, so the total extension or the total elongation of the spring in the second case, that means when you release suddenly, this is the formula. mgx is equal to half kx square. You have to apply law of conservation of energy. Decrease in GPE of the block is equal to increase in the elastic potential energy of the spring. So x will be cancelled here. So x is equal to 2mg by k. This is the total elongation of the spring, and this is the equilibrium elongation. The difference will give you amplitude, always remember, x minus x naught. That is 2mg by k minus mg by k. So that is equal to, so mg by k. This is the amplitude. This is the amplitude A. Again I will repeat. When you connect a block of mass m to unstretched spring, and if you release it slowly, it will come to equilibrium position. If you release it suddenly, so it will execute SHM. What is the amplitude of that SHM? So total elongation in the second case, that means when you release it suddenly, total elongation of the spring minus equilibrium elongation of the spring will give you the amplitude. So after this, when springs are connected, so like this, at some angle, then so here actually the block of mass m is connected to, so three springs k. So they may have equal spring constant, or they may have different spring constant. How to solve such problems? See here. Here we release block. So here we have a block of mass m. That block of mass m will be displaced, so along this line downward. When the block is displaced along, so this line downward, you extend that line of oscillation, then say this is theta, this is also theta. So if x is the displacement of the block, then the total force acting on the block will be kx plus kx cos square theta plus kx cos square theta. Remember. Here the total angle 2 theta is 120 degrees. Theta is 60 degrees. So F is equal to kx plus kx cos square 60. So it is 1 by 2. So 1 by 4. So cos 60 is 1. You get children here kx plus here 2 times of kx divided by 4. So that is kx plus kx divided by 2. That is equal to, so 3kx divided by 2. So is the force. So once we get force, so you can also equate this force to k dash x. So what is that k dash x here? What is that k dash value here? So that k dash value is equal to 3k by 2. 3k by 2. Now the time period is given by 2 pi root over m divided by, so 3k divided by 2. So that is 2 pi root over 2m divided by, so 3k. This is what you get, children. So that's all in this video, children. Thank you.